Today's topic is sintering of ceramics. Well, sintering is one of the most important steps and also a unique phenomena in manufacturing of ceramic products. As you may be familiar with other production techniques or fabrication techniques for other materials like metals or alloys, they can be melted and cast when required, forged or machined to attain the final or the useful shape. However, for ceramic materials which are having a relatively high temperature or high melting point, it is difficult to melt, and therefore, it is difficult to cast or give it a shape by molding process. And at the same time, the ceramics are also brittle, and therefore, it cannot be forged. So, they do not have any plastic deformation even at very high temperatures, and therefore, the fabrication, the normal techniques of fabrication as used in metals and alloys or even plastics cannot be applied to ceramic materials. So, of course, ceramic materials are also sometimes melted and cast only under very special circumstances and when it is absolutely necessary for some developing certain properties, but obviously they are quite cost intensive and normally avoided. Fortunately for the ceramics community, sintering provides an alternative and useful process for the shaping and consolidation of ceramic materials. Since normal melting and casting cannot be done, or forging cannot be done, or rolling cannot be done. So, one needs a completely different approach for giving a shape and size or manufacturing a particular product out of ceramics. The ceramic materials are particularly the raw materials are available in powder form. Well, there are one of the major reasons is ceramics is basically a brittle material. So, it is and the naturally occurring materials are lumpy and they can be ground to fineness, and at the same time, so far as the advanced ceramic products or compositions are concerned, as we have discussed earlier, they are all synthesized, they are not naturally occurring, and during synthesis, particularly chemical synthesis, we do get powders. So, for ceramic materials, it is the raw materials are basically in the powdery form, and because these materials are brittle, even the lumpy materials, naturally occurring lumpy ores, can be ground relatively easily, and that they may be the starting powders or starting raw materials for the ceramic fabrication. Powdery raw materials are at the same time provide several important advantages, and that is the reason this sintering has come up. The phenomena or technique of sintering has been developed. They can be suspended in a liquid, and suspension can be used for the casting to give them a shape. Well, although they are not plastic materials and they cannot be melted, but these powders which can be suspended in some kind of a medium, liquid medium, maybe aqueous or non-aqueous sometimes, and one can form a slip, a viscous slip, and that can flow and fill up the cavity of the molds, and therefore, one can develop casting techniques with the not with the use of molten material, but with the suspensions of the fine powders, and that is a very common technique, even starting with the slip casting to gel casting and tape casting and so on. So, powder materials have their own advantages in that context. Powders can be directly fed into a mold and pressed to a shape, particularly at high temperature, high pressure. So, there is powders can be also have a free flowing characteristics, or it can be made free flowing by certain additives. Some binders can be used, and then a high pressure can be applied into a mold, so that the powders can take the shape of the mold. So, that is another way of using the powders to give it a particular shape, even if these powders are really not plastic or cannot be melted. Given an opportunity, which means making available a sufficient activation energy. So, if sufficient activation energy is provided to the system, these compact powders, the powders tend to lose the excess energy associated with their free surfaces. This advantage is made use of in sintering. So, the powders, when they are heated to high temperature, so that certain activation energy is provided to the system, they tend to lose their energy, the excess energy, because of the high surface area, the surface energy particularly, and this is the technique, or this is the process which is taken advantage of in sintering. So, in sintering actually one provides certain activation energy by heating to high temperature, so that the excess free energy because of the surface area, high surface area, it can be removed and the particles can bonded together and a strong bond can be developed. So, we will discuss that, and that is one of the basic steps or the basic phenomena of sintering. So, if you would like to have a definition of sintering, there is no unique definition. In fact, people have used different kind of approaches to define what is ceramics, what is sintering. Sintering is a process by which a powder compact is transformed to a strongly bonded monolithic mass with the removal of interparticular pores. To start with, obviously the powders, when they are compacted, they cannot be completely pore free. There will be some pores and or free surfaces available. So, this process of sintering, by sintering at a high temperature, what we do actually, or what the changes takes place in the material is they are strongly bonded, so to get transformed to a monolithic bond, a monolithic mass with the removal of interparticulate pores. So, in the sintering, one way of looking at sintering is basically removing the interparticulate pores and making a strongly bonded material. They no longer remain powders, but the powders get coalesce with each other and make some strong chemical bond, and that is how the process of sintering can be described. It may also be considered as a process through which small particles or a cluster of particles of uniform composition undergo changes in shape and size when heated to a sufficiently high temperature. It is basically the effect, the whatever changes takes place. We have looked into earlier that there is a change in the pore structure, the pores are getting removed. This is also the same thing, but in from a different angle, looking at from the different angle, there are particles or a cluster of particles of uniform composition. What has been added here is a uniform composition, undergoes changes in shape and size when heated to a sufficiently high temperature. So, that is also a process of sintering, or can be called a definition of sintering. Sintering is a complex phenomena in which several processes occur simultaneously. It is not exactly the definition, but what exactly happens and how it can be described. The sintering is a complex phenomena in which several processes occur simultaneously, but the final outcome is as mentioned above. So, it is really from these 3 points one can see the exact definition of sintering is really not there. Various researchers or various engineers have looked at it from a different point of view and described the phenomena in their own ways. Now, why the materials get sintered? That means, why the pores get removed, and a loosely bonded compact, what sometimes referred to as green compact, without heating to high temperature. So, they have a very low mechanical strength and not useful for all practical purposes. But when you heat them to high temperature, you do get a very sound material, a mechanically strong material, a non-porous material, and it is as good as any other materials like metals or plastics. So, it becomes a very sound material instead of a porous material. It loses its porosity, and the particles get bonded together and a strong bond gets developed. So, there must be some driving force, and this everything happens just by heating the material to a high temperature. So, something must be happening, and there must be some processes taking place for which there must be a driving force, and there must be a tendency, thermodynamic tendency for changeover to take place. So, if we like to look at what is the driving force of sintering, it can be mentioned in this manner. The macroscopic driving force for sintering is the lowering of excess energy associated with the free surfaces of the fine powders. Any fine powder, whether fine or coarse, does not matter, powders have a high specific surface area. That means, the area, surface area per unit weight is much larger than a solid material of the same mass or same weight. So, it has a very high surface area, and all surfaces has certain amount of surface energy. So, it is obvious that the fine particles or fine powders do have a very high surface area and surface energy term. So, when you compute or try to look at what will be the overall free energy of the system, the free energy of the system is dominated by the surface energy term compared to a solid material. So, compared to a solid material, powders do have a extra energy in the form of surface energy. So, if an opportunity is given to the system, it will try to lower its surface energy and also the free energy of the system, and therefore, the macroscopic driving force for sintering is nothing but the lowering of the excess energy associated with the free surfaces of the fine powders. Now, this may occur in different ways, this lowering of surface energy. The reduction of the total surface area through increase of the average size of the particles. Okay, nothing happens, no bonding takes place, but some materials, some finer materials get coalesce with each other, so that the average particle size increases, but there is no strong bond gets developed. So, by that process also it can reduce the surface area and surface energy term. So, this is one of the ways to look at the system where the particle size is just growing, but the interparticulate bonding is not really taking place. So, this kind of a process if it happens, so if somebody takes just the loose powders, not compacted powders or strongly bonded at the green condition before firing. We have said earlier that normally the powders are consolidated by applying pressure or by some casting techniques. So, if that is not done, just the loose powders getting heated together, there may be particle coarsening, but though no mechanical strengths really get developed. So, that is one way by which the surface energy term can be reduced. The other possibility is the replacement of high energy solid vapor interface by low energy solid solid interface formation, and that is nothing but what we call the formation of grain boundaries. That means, the particles or the fine powders, when they are free, they have a surface area, and that surface is nothing but the solid to vapor phase, the solid to vapor interface, that means with the air in this case. So, or one can say solid gas interface. So, that is one kind of surface which has certain amount of surface energy, no doubt, and if that is replaced by a solid solid interface, that means the gas, the intervening gas is removed and the solid two solid particles comes in contact with each other and form a strong chemical bond between them, then the gas interface is no longer there. So, there is no solid vapor interface, instead a new interface has been formed by way of formation of a grain boundary. So, the solids two particles by some means, in fact, that is called the process of sintering, they come closer to each other and slowly there is a interatomic or interparticular transfer of certain atoms, and we do get a chemical bond. So, that kind of bonding give rise to what we call the grain boundaries. So, the two crystals, in fact, the particles can be considered as two different crystals. So, they will come each other and form the bond, so that the intervening vapor phase is not there. So, the vapor, instead of a solid vapor interface, we are creating solid solid interface. So, that is a grain boundary. It is also an interface, it also is associated, it is also associated with some kind of surface energy, because the surface is very much there. So, but this energy term, the surface energy for the solid solid interface is lower than the solid vapor interface, and that is also the driving force. So, there is always a tendency to lower the overall free energy or the overall surface energy term, and that surface energy term can be reduced by replacing the solid vapor interfaces with solid solid interfaces. So, that is another driving force for the sintering. Both the phenomena may occur simultaneously, or one may lead the other depending on the local situations. So, locally whatever the situations are there, what kind of experimental parameters are there, depending on that both of them can do then can proceed simultaneously, or one can precede the other, one can lead the others. So, but these are the two primary driving forces why the sintering should take place in a powder compact of ceramic materials. Now, these are the pictorial representation of what we have just discussed, what is the driving force, what is coarsening, what is grain boundary and what is the overall process of sintering. Here this shows the particulate compact, the agglomeration of particles or the compacted particles, they are loosely bonded at those interfaces, and this one can say that there is a solid solid interface, but this amount of solid solid interface is very low, very small compared to the solid vapor interfaces. These pores or the boundaries of the pores actually provides the solid vapor interface areas. Now, if this is our initial particulate compact, there are three ways of what can happen if we heat to high temperature. One is the very simple one which we have described earlier, that is the particle coarsening. If we look back, this was the reduction of the total surface area through increase of the average size of the particles. So, that is called the coarsening of the particles, and this is given here. So, the particles are there and each of these particles grow. Of course, in reality, although it has been shown that all the 7 particles here have grown, but in reality that does not happen. Some of the particles grow at the expense of the others, because the overall mass remains constant. We are not adding any mass to the system. So, the overall mass remains constant. So, obviously, for mass balance, some of the particles will grow at the expense of the others, some others will dissolve. So, that is not shown here unfortunately, but basically what we are showing here, that particle size grows, but the contact area does not change much, and there is no mechanical bond or chemical bond taking place. So, the overall surface area reduces because of the larger or the coarser particles, that is why the surface energy term reduces, but the strength of the material do not change. So, this is what we call coarsening, and delta A means basically A is the area. So, there is a change in area, but there is no change in the surface energy term, or whatever surface energy term will be reduced is because of the area. There is no qualitative change in the type of the surface. The other alternative is what we call the densification. That means this kind of a loose powder changes its configuration and makes a strongly bonded powders. So, they are now strongly bonded, the size and shape have changed, and there are greater surface particle to particle contact or solid to solid contacts. So, these white lines are actually called the grain boundaries, and the pores, the larger pores have gone out. So, this is more compact and dense material compared to this aggregate. So, as a result of this we call densification, that means pores have been removed. So, because the pores have been removed, the average density has increased. So, the material becomes more dense, and once the density increases and the grain boundary the grain boundaries are formed, you have a strength is also developed, and greater mechanical strength is also gets developed. So, in this case actually the quality of the surface changes. So, there is a change in gamma, the surface energy term, surface area or the specific surface energy changes, because the nature of the surface had changed from primarily from solid to solid vapor surface. Now, it is a solid surface. So, this contact is actually solid contact. So, this surface energy term is different, it is a lower energy term, lower energy surface, and that is the driving force for that. It may also happen that both of them both coarsening and densification proceeds simultaneously. So, densification and coarsening can proceed simultaneously, and finally, you will see the size of the grains have increased, size of each particle has increased from this size to this size, and also the contact area have changed. Contact area from kind of a point contact, here we have a quite large surface contacts, and these are once again grain boundaries as in this previous one here. So, here it was only one process happening, here another process is happening, and diagonally we have simultaneous processes of coarsening and densification. Now, under certain circumstances this can also happen. It can follow first step in a step by step, it goes to the densification first, but without much grain growth. The grains are relatively small, it is almost like this, the grain size is almost like this, the individual particle size is, although their shapes had changed, but the sizes, average size is more or less same. But afterwards, if you continue to heat or provide sufficient activation energy to the system, the smaller particles may grow to the larger particles, and that is what we call the grain growth. Now, grain growth here, once again the driving force is basically change of surface area, not the surface energy term, but the surface area. Here it is surface energy and surface area both are changing. So, this is also another possibility, but in principle this is not so feasible, because once these larger particles are there, the sintering itself becomes difficult, and it may not reduce its pores so easily. So, until and unless one goes to a very high temperature. So, once that coarsening takes place, the pore removal becomes quite difficult. That is the reason from this step to this step is not really quite feasible, although it can come via this step to this step or directly from these steps through a diagonal route. So, these are the different possibilities what exactly happen. We have considered two different phenomena here. I mean both of them are constituents of the overall sintering process. One is the coarsening process, particle coarsening process, and there is the densification process, which our interest or we prefer to have more densification than coarsening. Now, two most important sintering processes normally we look at it from these points of view. First is the solid state sintering, that means the direct particle to particle contact. There is no intervening other phase, except of course there is a vapor phase all the time present. Whenever there is a pore, there will be some vapor phase or gaseous phase there, either air or something else. So, the very important mechanism or the sintering process is solid state sintering, and that is really prevalent in most of the materials. Of course, not in traditional ceramics. In traditional ceramics, of course, the solid state sintering is not so prevalent, but in advanced ceramics it is quite prevalent. Whereas, there is a liquid phase sintering also. That means, in addition to the solid particles, we are talking about basically solid particle coalescing with each other or making bonds with each other, but we may take help of a liquid phase. Just like an adhesive, we do stick two different materials by an adhesive. So, here also a liquid phase can be used as a kind of adhesive. So, the presence of a liquid film, particularly at high temperature, ensures adherence of the solid particles together. So, that is normally called a liquid phase sintering. So, we take advantage of a liquid Liquids are normally more adherent and they have a good wettability with the other solid surfaces, and by choosing the liquid composition one can have a good bonding. So, that is another a very simple or a common technique of sintering. And both the things, of course, in both the cases there is a bonding between solid and solid, because this liquid whatever we are taking advantage of at the high temperature, ultimately it becomes a solid at the room temperature. So, that is another way of taking care of the sintering process. Basically we want to strengthen the material and remove the pores. Now, this is a pictorial representation of what happens in case of solid state sintering and liquid phase sintering. This kind of representation we have already seen in way of grain boundary formation. So, in a solid state sintering, basically the loosely consolidated powders directly goes to grain boundary formation. We are not talking about any coarsening or anything like that. Coarsening may take place, may not take place, but finally the final structure should be like this. That means there is a direct grain to grain contact or solid to solid contact, and overall area of the contact area should increase. So, that is the solid state sintering. Here is a liquid phase sintering. That means we are taking some material within the green compact, some material which can form a liquid at a relatively high temperature. At room temperature, of course, it is a solid and it behaves like any other rest of the particles, but so far as this consistency is concerned. But at high temperature this will melt fast, and this will not melt, this will still remain solid, but this will melt and form a liquid, and so a pool of liquid forms in between the solid particles, and the pores get filled up with the liquid. And also because of the high wettability factor of this liquid, so this bond is formed. So, there is no direct grain to grain contact or solid to solid contact, there is a intervening film which actually takes care of the bonding and strengthen mechanically, provides the mechanical strength. So, the mechanical strength in this case will of course depend on the mechanical behavior of this bond phase. So, it is a kind of bond between the particles, solid particles. So, that is the basic difference between a solid state sintering and a liquid phase sintering. Now, we have talked about the surface energy term, and we have talked about both the solid vapor surface energy and solid liquid surface energy. Now, there is a concept of what we call the dihedral angle, the surface energy and dihedral angle. Whenever there is a surface energy term and two surfaces are coming in contact with each other, there is a dihedral angle. So, we will discuss that just now. A necessary condition for sintering process is that the grain boundary energy, that is the solid energy, surface energy, or in other the solid surface energy should be less than twice the solid vapor surface energy, that is comes out from that particular geometry. This implies that the equilibrium dihedral angle, which is phi, is required to be less than 180 degree for the sintering to take place. Now, what does it really mean? We have a, from this diagram one can see this is a solid surface. Of course, it is not circular, it has not been taken as circular. Here is of course a curvature or radius of curvature, and there also another radius of curvature here. Now, this is in the midway of, let us say, the sintering process, when it is on, this is air, this surface is air or some vapor. So, this part of the solid, if we consider this is one particulate or one surface, originally everything was exposed to the vapor phase, and slowly the part of the surface is coming or growing in such a way that the vapor phase is eliminated and a direct solid to solid contact develops. So, this becomes our grain boundary then. This is solid to vapor surface, so is still exposed to the vapor or the air, and here also the same thing. So, this is one particle and this is another particle, and slowly this grain boundary gets developed, so that the vapor phase is eliminated from that region. So, if we look at the surface energy terms, this is the grain boundary. So, the surface energy term is gamma GB, grain boundary, and these are the two tangents. These are the two tangents at the interface or at the point of intersection, and the type of radius it is formed here. So, this is one tangent and that is the another tangent, and these two tangents, along these two tangents actually the solid vapor tension, vapor phase, the surface tension terms acts. So, this is one tangent, this is another tangent, and the angle between them is the phi, and that is called the dihedral angle. So, if you have a pair of tangents on the two surfaces at the point of contact or point of formation of the grain boundary, then that angle, particular angle, is called the dihedral angle, and one can see this kind of an equilibrium. This is downwards, whereas these two are upwards, and this gamma, the gamma GB is equilibrated with the two tensile forces term, and this is phi by 2. So, the component along the perpendicular direction is actually gamma SB cos phi by 2. So, twice, because there are two surfaces, so twice of that must be equal to the gamma GB. So, the angle will be determined by these two terms, the ratio of these two terms, and as per definition this grain boundary must increase and the other two must decrease in the sintering process, and therefore, it says that it should be less than 180 degrees, phi must be less than 180 degrees. So, that this becomes around phi by 2 is 90 degrees, it must be less. Normally in materials is around 120 degrees. Okay. So, that is one precondition from the surface energy points of view. So, these values of the gamma GB, grain boundary surface energy, and the solid vapor surface energy, these two terms are certainly important to determine whether the sintering process will proceed or it will not sinter at all. So, that is purely from the surface energy point of view, and surface energy some surface energies have a very important role to play in sintering process. That was for solid state sintering. If you have a liquid phase sintering, then it is actually the surface is not solid to vapor, here is solid to vapor, but there is a solid to liquid interface, because there is a pool of liquid present, and that liquid in contact with vapor, but the vapor is not directly in contact with the solid of our concern, of our interest. So, here also is the same thing, same kind of conditions apply, and instead of phi we call it psi, and this again the same condition applies here. Only thing, the surface energy term here is gamma SL, the gamma GB is the grain boundary once again. Once the grain boundary has formed, when the grain boundary has formed here, we are still assuming that although the liquid is there, but in this case it is not, liquid is not forming the grain boundary phase, or there is no film of liquid along the grain boundary. So, this is slightly different concept than the liquid phase sintering which we have used earlier, or we have defined earlier. Liquid phase sintering, we have a film of liquid, but here in the pool of liquid ultimately the liquid is not along the grain boundaries. Grain boundary is formed on its own, it is a solid solid interface, and it is not a solid liquid solid interface. So, it is basically a solid solid interface, but growing out of the solid liquid interface. So, solid liquid interface is getting eliminated and solid solid interface are getting created, just like in case of solid state sintering, where solid vapor phase interface is getting eliminated and solid solid interface are created. We have just discussed two different techniques, two most important techniques which normally occurs in different materials. One is solid state sintering, the other is liquid phase sintering in presence of a liquid. Of course, there are different variations in addition of the liquid phase sintering also. We may discuss later on what are those variations, what kind of liquid it is it a reactive liquid, it is not so reactive liquid, and so on. In addition, you have few more types of sintering where some of the parameters are slightly different. For example, high pressure sintering. Well, what we have discussed earlier is basically a atmospheric sintering. Although there is a presence of vapor, but the vapor is present in atmospheric condition. So, it is not it is really, one can say it is a pressure, sometimes it is called pressureless sintering, but one can also use high pressure gas pressures at high temperature. So, the reaction or the sintering process can take place under high pressure of gas pressure. So, that is called high pressure sintering. We will discuss briefly later on, just mentioning here what are the other variations possible. Reactive sintering, primarily this is not a pure sintering, but a combination of chemical reaction and sintering. Sometimes in presence of a liquid phase, it may not be in the presence of a liquid phase also. So, there are chemical reactions between the reactants, between the different powders. So, it is not exactly the normal sintering. In normal sintering, we have assumed that the chemical composition of all the powders are identical, but it may not happen so. In some cases, we do have different powders of different compositions, and that those different compositions may have some chemical affinity towards each other, and that is not only sintering, but a chemical reaction is also taking place simultaneously, and therefore, that kind of sintering process sometimes are referred to as reactive sintering. In addition, we have microwave sintering. The only difference here, of course, the mechanism of heating. The heating is different. The way the product or the compact is heated to high temperature is completely different. This we will discuss later on, what is the advantage or disadvantage of microwave sintering. Okay. Every material cannot be heated by a technique of microwave, by applying or exposing it to microwave. There are certain dielectric characteristics required for microwave sintering. So, but if those characteristics are met, microwave sintering is one of the very good sintering heating process. So, by that heating process one can get also sintering, because the heating is one of the prerequisites of sintering. Spark plasma sintering, well, it is a relatively new technique where you apply certain pressure and also at the same time apply a very high DC voltage, so that at a local level there are minor sparks generated. So, the temperatures are goes up very high, particularly at the surface of the particles, because of the high surface energy, the sparks are basically generated at the surfaces, and therefore, one can have a different kind of sintering or the surface reactions at those interfaces. We will discuss briefly at a later stage. Well, having looked at what are the different preliminary mechanisms or preliminary variations of the sintering process and what are the driving force, let us look at what are the ultimate outcome of the sintering process. At the end of the sintering process or at the end of exposure to high temperature, what do you end up with? These are few things which actually happen as a result of sintering. Two things of course are very common. One is the volumetric shrinkage and there is densification. So, volumetric shrinkage means the pores getting reduced. So, the particles coming closer to each other, and as a result there will be a volumetric shrinkage. Whatever the compact volume was there to start with, after sintering the size certainly should be smaller, and consequently the volume gets decreased. So, the mass remaining same, you have a densification process. So, these are the two most important things happen in most of the sintering processes. Associated with that, there are few others. Reduction of pore volume and size. Once again the volume gets shrunk. So, the pores are actually is reduced, not only the overall pore volume, but also the size, and that also has an important consequence so far as the physical properties of the ceramics are concerned. So, you have a reduction in the pore volume as well as pore size. Average size of the pores decreases, and that is very important. Significant enhancement in mechanical strength, that is another very important, in fact one of the basic purposes of sintering the material is to enhance the mechanical properties. Otherwise, the powder compacts are very weak and they cannot be used for any practical purposes. So, that is another thing we expect at the end of the sintering process, significant enhancement of mechanical strength. Other thing, particularly at the looking at the microstructure or what happens to the powders, the grain coarsening if not controlled. Grain coarsening and particle coarsening is slightly different. We have seen particle coarsening without sintering. Here the grain coarsening is basically grain growth. Okay. So, the grain growth takes place at a high temperature after the basic sintering process is over. So, the particle contact has already taken place. So, the contact area have increased, but even after that if we allow it to expose it to high thermal energy, there is further reduction in the surface area. Even the solid interfaces gets reduced, the area of the solid interfaces gets reduced. That means the crystals, each individual crystals grow to a large extent, and that is called grain growth. Sometimes the grain growth is good for certain purposes, but for many particularly for mechanical properties, grain growth may not be always good. So, you need to control that size also, that aspect also. So, these are important outcome of the sintering process. Oh, that we have already considered. I am sorry. This is something again a schematic representation of what kind of, we have already mentioned that there is a shrinkage, the volumetric shrinkage, and this is just a time versus shrinkage curve, or the shrinkage versus time curve. It is an axial shrinkage, linear shrinkage, it is not volumetric shrinkage, and two are related quite obviously. So, this is a linear shrinkage which is normally measured, volumetric shrinkage are basically computed from the linear shrinkage data. So, one can see initially there is a sharp little sharper rise, that means the slope is little large. So, there is a first shrinkage takes place at initially, but then slowly with time it tapers off and becomes almost constant. So, after some time the shrinkage is no longer taking place further, and it comes to a permanent a constant value. So, but if you increase the temperature, these are two different temperatures, one is a relatively low temperature and there is a high temperature, and the curves itself says that at high temperature the initial rate is very fast and then tapers off and becomes almost constant over independent of time after some time. But if you take at a low temperature, then it continues for a longer time, and then finally of course it comes to a constant value. So, this is normal behavior of any ceramics, and how the typical shrinkage proceeds with time and temperature. This is a schematic grain size versus density variation, that was with time. Here it is not time, but as a function of the percentage shrinkage which has taken place, and how the grain size changes. Now, in this case of course, there may be three different possibilities. Had we have discussed earlier in the very beginning pictorially. What happens to the powders? Either it may coarsen, that means the powders can grow themselves without any sintering. They can powder can get sintered, grain boundary is formed, and then later on grain growth can take place. And here this is something little intermediate, that means coarsening and densification proceeds more or less simultaneously. In that case, we have three different curves or three different effects you can gain so far the grain size is concerned. Now, grain size initially is the starting material is relatively fine grain, or there is hardly any grains to form, but as the theoretical density increases, that means more and more sintering takes place. Theoretical density means you are eliminating the pores, and so you are increasing the mechanical strength also, which is normally directly proportional to each other. So, the theoretical density, percent theoretical density, no, it is a percent theoretical density, means initially 0% to about 100% density, that means 100% dense material. So, you have three different situations as I mentioned, coarsening plus densification. So, there is a gradual growth of grain size as as the density increases, as the pores gets removed, more and grains are also grow simultaneously. So, this is more or less a preferred situation where both the things should be controlled in a manner that they grow with each other. This is not a very good situation where theoretical density has not grown, but the grain size has grown very fast, and as a result what we will get is a very poor mechanical strength here. So, this is not a preferred, neither this one, because high grain growth leads to many different problems, primarily more brittleness, and we will see later on how the mechanical behavior changes as a function of grain growth. So, normally grain growths are not a very preferred situation, except under certain situation, if you are talking about a transparent ceramics and so on, sometimes grain growth are preferred, but there mechanical properties is not that important, it is more of the optical properties which are of interest to us. So, there one can allow grain growth, but normally for most of the purposes this is a preferred situation where coarsening and densification grows simultaneously. Well, so that is more or less half of the sintering lecture we have completed. Rest half we will take it up in the next class. Thank you.